All right, here we go, everybody. Newton's third law of motion. All right, it's super important, kind of tricky to understand. And even when you think you understand it, you end up getting tricked later on. That happened to me. Student teaching in Brockville at TIS, and a student asked a question, and I thought I understood it, and it stumped me. So I'll get to that question later in this lesson. All right, so I'll share that with you when we get there. Newton's third law. So Newton's third law intro here. Think about forces when the blue cart collides with the red cart. Okay, so we're going to observe and think about. So we're going to observe the acceleration of the carts, and then talk about the forces on the carts. And I didn't put my link in here yet. I'll just grab the YouTube link itself here. 1 sec. I didn't put that in there yet, but that's okay. I can go to my videos and recently added here. Here it is. Blue cart colliding with the red cart. Here we go. Just we see what's going on there. Out. Very obvious kind of stuff. You've seen this with like pool balls and stuff like that. Maybe if you play pool and things like that. So physics is all around you, and we'll get better at understanding it. So the red cart obviously accelerates away, right? Since the blue cart pushes to the right on it, it accelerates off to the right. Great, right? And sometimes, I'm trying to get students in a class to think about other things as well, right? So if I just said that and be like, okay, we're done, lesson over, be like, someone in the class might say, well, wait a minute, the blue cart also accelerated, right? Because it slowed down and stopped. And so it accelerated in the negative direction and caused it to slow down, right? So it must also have a force on it, right? And so that force is, of course, the force of the red cart on the blue cart. But if you think about it, like we talked about here, we sent the blue one in and the blue one hit the red one. A lot of people think that's the only thing that's going on. And so we're identifying the fact that, actually, when that happened, there was a force of the red cart on the blue cart back. And that is your reaction force. Okay? So we've got the action force of the blue cart on the red cart. Let's do this. Let's do action force. Right? The action force was the force of the blue on the red. And then the reaction force was the force of the red on the blue. Okay, this one, let's just point out and recognize the fact that this one is obvious. Right, it's the force of the bat on the ball or whatever, right? And then this one is the one we have to remember exists. So, this one's not as obvious. And details about it, depending on the situation, are not as obvious either. And that's the whole point of this lesson. Newton figured this stuff all out and then tried his best to try and help everybody else learn about it. Okay? Well, here we go. I'm carrying on that tradition. So, question, the Office fans, question, what kind of bears best, right? I mean, how big are the forces? How big are the action and reaction forces? Okay, so think about it in this situation. We can go back to the video again and look at it. We've got the blue cart coming in, pushing on the red cart pushed on the blue cart, and so on. So how big were those forces when that happened? Okay, so let's look at this situation here. They accelerate the same amount, obviously, just in opposite directions because they have the same masses. Like one, you can just tell looking at it, right, that they had one sped up and one slowed down, but the red one ended up with the same velocity as the blue one. You can just sort of tell. Now, we can do better than just sort of telling. Here's a version of it that I did at home, I think during COVID. So that's just yeah, there we go. So that's the blue one coming in, hitting the red one, same stuff, right? And then let's look at the results. Okay, so let's look at the video of the actual forces. Because of the technology that we have available to us, we can see that interaction, same as what I just showed you. Then zooming in here, you can see, oh boy, I needed to pause that just at the end here. How do I get this to pause? I have a picture of it in my lesson anyways, but there we go. So we have a force of about 1.5 and about 1.5. One in the positive direction and one in the negative direction. Right? So you can see they're about 1.5 or so, right? So we are seeing here that they're both about 1.4 or so, 1.5 or so, sorry, in size. And so basically we're seeing that the action force, the blue card and the red card, is equal to the opposite of the reaction force, or actually, I kind of like to say it the other way around, to be honest. Let's see if this is a piece group. So really the reaction force is equal to the negative of the action force, right? Because the action force is the one that's obvious, right? The force to the right on the red car. And then so the reaction force is equal to the opposite of that, which helps you realize that there's a force to the left on the blue card from the red card. Okay? So we have these numbers, but either way, wherever the negative was, this one, if I leave it this way for now, just because it's all set up like this, we have the negative of that force to the left, right? And so if you think about it, that means that we have equal forces, equal values, let's say, right? We don't have to do that part really, but anyways, they're the same. Long story short, right? So just as a little warning here, I'm setting you up for a trick question. So they accelerate the same amount, just in opposite directions. So they have the same, and of course it's the same forces, right? I'll just put it that way. It is dangerous to get tricked into equating the effect a force has with the size of the force. Okay, so what I'm pointing out here is in this case, this is obviously true, right? We have they're accelerating the same amount, and it was the same forces, right? Not wrong, but let's go to other cases. We'll come back to that maybe if we need to. All right. So what about now? We've got this cart loaded up with 3 extra masses. So this is actually 4 mass units, if anybody's into chemistry. Not atomic mass units, of course, but anyways, 4 units of mass, essentially. That's how they designed this thing, hitting 1. They have like a 4-to-1 ratio, but it doesn't matter for what we're talking about. But anyways, we got a heavy one colliding with a light one. Well, what's going to happen here? Let's see this one. Got my link in here ready to go. Okay, so play that again. Heavy one comes in, hits the red one. The red one goes flying off faster, right? Obviously. And then the blue one even actually keeps going. Okay, so if you're looking at that, the red one got more velocity this time, and the blue one did not fully slow down to a stop. And so obviously this one accelerated more than this one. This one accelerated less than normal, and this one accelerated more than normal. Okay? So in this situation, obviously we have that we have less acceleration backwards and more acceleration forwards. Let's go to the case where we have a light one colliding with a heavy one. Okay, so light one colliding with heavy one here. Let's just replay that. So we got light one coming in. This one ends up, the blue one this time ends up going backwards. So it accelerated backwards way more, didn't just stop and end up going the other way. And pretty clearly the red one goes off slower this time than normal. Okay, than that first time we saw. So these are just visual things you can see, right? So obviously this one has way more acceleration backwards. It actually made it end up going backwards as a result. And of course, less acceleration forward. So the experiment results that we're going to see here. So let's look at the big one hits the small one. COVID days, but wasn't worth redoing this video because it's kind of tricky. So there's the big one hits the little one. Okay, I don't really need to show that, I guess, because we already saw it ourselves. Let's go to the one that shows the results. So big one hits the little one. Little one flies off with a fast speed, faster than normal speed, so it had more acceleration. The blue one slowed down a little bit this time, so it had less acceleration. And zooming in on the graph here, we see, if I can stop in time here, boom, around this much acceleration this much force and around that much force. They're both right around 4 or so, right? Within margins of error, you can tell they're both about the same. Clearly one isn't a heck of a lot bigger than the other one, right? So what we're seeing is right here, we're seeing that, of course, the red one accelerates more and the blue one accelerates less. Forces result, though, they were both about 4 newtons. So now we have action force equals negative reaction force, or vice versa. And so we have the 4 equals negative 4. We got this idea that we have these equal sizes of forces, just opposite directions. Again, I don't really need the double negative there, but anyway, so equal forces. And then you're like, okay, wait a minute. Oh, and I'll show the other one too while I'm at it. So this one, of course, they were the same force. And then let's go to the down here, this one, less mass hitting the big mass. Let's go that. So less mass hitting the big mass, right? And so again, we saw here it wasn't as drastic of a collision because I only had the short track at home. But the red one only speeds up a tiny bit. The red one ends up, the blue one ends up going backwards. And again, same forces. They're extremely similar values, right? The force sensor on each cart is literally just showing us what the forces are on it. So again, here, even though the red one accelerates only a little bit and the blue one accelerates a lot, we ended up with these same forces. They're both about 2.8. And so we have action force and reaction force being equal and opposite. Okay. So the conclusion here is that they're the same also. And so what we're leading to is that they're the same always. Okay. So the lead in here was, hey, the same amount of acceleration and they were the same forces was true. Here we're ending up with, where am I going here? Here we're ending up with different effects, but of course the sizes, well, the sizes are the same. Okay, so the masses being different changes the effect that those equal forces have, and I've got another page dedicated to that as well. In case you need another clarification, right? So how can the forces be the same if the accelerations are different? The answer is, well, easy. They're on different masses, right? So don't be tricked by the difference between the size a force has and the effect it has. Don't look at a force having way more of an effect and then assume, therefore, that it was much bigger, right? Because instead, it could be the mass was smaller. So mass matters, of course, right? So our conclusion, which is Newton's third law, I don't know what that box was there for. Newton's third law is that for every action force, there is an equal and opposite reaction force. And then we could add to this, even if the effect of the forces is not the same, F equals ma, people, so if you have a large mass, it's going to accelerate less with an equal force. If you have a smaller mass, it's going to accelerate more with equal forces, right? So it leads to, answers to questions being the wrong if you're not thinking carefully about it. Okay. So third law of motion, we know this, equal opposite reaction on the first object. So don't be tricked by the different effects that they have. So let's just get used to pointing out action-reaction pairs. Obviously, we have an action force of the person pushing on the cart. So let's just put a spot there and say, okay, we're pushing on the cart. And then there's a reaction force of like the cart on like the person's hand, right? I'm being really careful here to show, but we've got an action force. So this is the force of the person or the hand on the cart. So again, action force is force of the hand on the cart. And then we've got here the force of the cart on the hand. So you can read that all right. That is your reaction force. Okay, and we're just going to do that over and over again until we get used to it here. So I mentioned bat on a ball before. Action force, the ball is actually like right here still. So there's the ball, right? It's got an action force on it, force of bat on ball. And was there a reaction force of the ball on the bat? Well, yeah, it actually broke the bat, right? So there was a force on here that was the same size, opposite direction. Let me just make that a skosh bigger, as they might say. So same sizes, right? And that force on the bat, like that. There we go. So we have the force of the ball on the bat. And again, this is the red one's the action force, and the green one's the reaction force. And there's tons of pictures I can find and that are just impactful, literally, no pun intended, that make this obvious, right? So, are any forces obvious here? Well, there's, I guess, the action. I'm not sure which one's the action force here. I guess you might think it depends if you're a soccer player. This person's facing the ball, I guess, instead of heading the ball. So I guess you could say the action force was the face on the ball. I don't know. I as a human being, I look at this the other way around. We have the action force of the ball on the face. So we have force of ball on face. But don't worry, there was a equal and opposite reaction force of the face on the ball, which you can tell because the ball is all crunched in, right? So we have the force of the face on the ball. But again, that's actually something soccer players do on purpose, just not so much with their face, right? So we have action-reaction pairs of forces. We want those to be the same size. So I'll just try to, good, right? And it's just, we just do this a lot. So we get used to the idea that these pairs of forces exist, right? So we've got the action force of the, the action force of the person on the wall, and then the reaction force of the wall on the person. Okay, so this is your action force, and this is your reaction. I should say force there as well. Okay, so action force and reaction force are color coded here. Action force, force. There we go. So we have action forces and reaction forces all the time, all around. You can see them everywhere. So we've got obviously here the action force of the foot on the block, the starting block, right? And then the reaction force of the starting block on the foot is the one that actually accelerates the person forward, right? So block on foot. We can point out that's the reaction force that accelerates the person forward. Right. So when you look at that picture, and if you ask someone who's really in tune with the physics and so on that's going on, you'd be like, what's the force that accelerates the person forward? A lot of people would say like, oh, well, the person's pushing on the ground. You'd be like, mm-hmm. And so what force is there on the person? Well, there's the force of the ground on the person, right? This one I like. So what happens when I made this up? Of course, I found pictures of people like crashing into each other, right? What happens when one Canadian bumps into the other, right? And of course, everybody knows Canadians, we're so nice, right? Both people apologize, and sometimes they almost wonder why, right? You end up apologizing for something that clearly was someone else's doing or fault. And one sec here. All right, sorry about that. So they both apologize, which kind of seems odd sometimes, right? But if you think about it, one person's apologizing for the action force and the other person apologizes for the reaction force. So Canadians just intuitively know about Newton's third law. It's a joke, but kind of funny. So label action-reaction pairs. We can do this all day long, really, right? We got the action force of the person on the diving board, or foot or whatever, but person on the board. And then and then we have reaction force of the board on the person. Which of course makes the person accelerate up eventually there, right? This one, there's this little wee spot here, right? We got the action force of the foot on the edge of the pool. So force of foot on edge. and the reaction force of the edge on the foot, right? Just get used to the idea of seeing that reality around you. It's not as obvious, I don't think, as until we really think about it. Right? So, question that was asked at TIS in the year 1999. 1999. Student teaching there. Actually, it might have been 98 because it was first semester. Anyways, not that it matters. Given that there's an action force always has an equal, every action force always has an equal and opposite reaction force, a question that sometimes gets asked, and if it does get asked, you need to be able to say an answer to it, especially if you're trying to teach a class. So some people ask how anything can ever end up accelerating. Like you have those people, I like to call them critical thinkers, right? So there was a critical thinker in my class in Brockville that asked this question, and I honestly I was stumped. I didn't know how to answer the question. I had to go home and like think about it. And that's exactly what I said. I'm like, I don't know how to answer that right now. Let me think about that and I'll get back to you. Okay. Well, what did I end up coming up with? You look back at all of our diagrams. Why don't these equal and opposite forces cancel each other out? And it's the most obvious answer in the world once you realize it. But pause, think about it, whatever. The answer is well, yeah. Why don't these cancel out? The answer is because they're on different objects, right? And so in class, I'll point out we have force of foot on edge and force of edge on foot. The only reason it's so hard to think of that is because those spots are touching and they're so close, right? But notice how I was deliberately showing like the force of the person on the edge, and then the force of the edge on the person, right? They're not on the same object there, right? So I get a student to you know have a textbook on the desk on the left side of the classroom, and I say, okay, push it to that side of the classroom, and then someone else on this side pushes with an equal force the other way. And so I'm like, okay, you pushed with 10 newtons to the left and you pushed with 10 newtons right. How come they managed to accelerate? Why didn't they cancel out? And of course the answer is really obvious. They're on different objects. And that's the same all the way through here. Okay? They're on different objects. They don't cancel out because they're on different objects. And that's the answer to that. It's obvious once you think about it. Here we have like a golf ball getting hit by a club, right? So there's a force of the club on the ball, making the ball accelerate. Force of club on ball. Then, of course, the reaction force is the force of the ball on the club. Right? And the baseball bat's kind of a better one where you can tell that there's a reaction force because it's like breaking the bat. Golf clubs don't usually get broken, just making sure they're the same size. So it looks good in the end. These are just videos of like golf balls flexing under the force. It just makes it obvious that there's an action force, but the action force is obvious anyways, right? So really the baseball bat one's better. So there's situations that we have to, like if I ended it there, you might end up still getting stumped by some situations. And so we have to think about a lot of different situations and be able to see how this is true in all these situations. All right. So warning, this one actually is rocket science. You know how they say like, oh, come on, it's not rocket science. This actually is. So warning, we've got a balloon that is, flying upwards, accelerating up because of these gases, that are shooting out this way. So we can explain this in terms of action forces and reaction forces. We have the force of the balloon pushing out on the air molecules. And what's the reaction force? We always can just reverse it, right? We have force of balloon on air, right? So like A on B, and we just reverse that to be force of B on A, right? And so just reverse it literally every single time. And so we have the force of the air on the balloon. This upward force, right? This one right here, force of the air on the balloon is the one that pushes on the balloon upwards, making it go flying up, right? This picture here, think about action-reaction pairs, right? And then, so you probably have in your head the idea of like the rockets are pushing on the particles that are flying down, and then the reaction force is the particles pushing on the rocket, and that's lifting the space shuttle. Hopefully that's the thought you have. Most people, if you see this launch situation and someone said, oh, so what's making the rocket go up? A lot of people would say that the rocket pushes on the gases, and then the gases hit the ground, and then that makes it push back against the rocket, and so it lifts. And you're like sort of half right, but mostly wrong, okay? Because if we look at, so yes, obviously the rocket pushed on the gases. That's part's good. But the gases simply push back on the rocket, sending it flying. There's no interaction with the ground needed. It's just a third law reaction pair. So if you look at this picture, you'd be like, okay, there's the rocket way up, like kilometers up in the air, right? Are the gases hitting the ground and as a result pushing on the rocket? No, it's just literally there's an action force on the gases. Reaction force is gases on the rocket. No ground needed at all. Okay. There are ground effects that have an impact if you're super close to the ground, but they're not necessary as part of the discussion. Okay, they just are necessary if you are close to the ground. I have a little toy helicopter that when it was low in battery power, it wouldn't fly in the middle of the room, but it would hover like 3 centimeters off the ground for another 5 minutes or something. And so it was like a little hovercraft at that point. So the ground effects of air reflecting back up and helping lift it. But yeah, so the gases hitting the ground are not part of the situation. Okay. If you have a Mack truck and a Volkswagen having a head-on collision, okay, which one will experience the greater force of the impact and when they collide? Mack truck, Volkswagen, they're both the same, or it depends on other factors. Depends on other factors might be a tempting one because you think of like, okay, depends on what material they're made of and stuff like that. But really, that's all of that's just determining the effect those forces have, right? And so, of course, the most common answer among people that aren't trained in physics would think that the force on the car is greater because the car gets totaled. But really, that's just this one. The force on it is having a greater effect. This is made of like flimsier metal, whatnot. Big, heavy-duty trucks colliding have very different results. But Newton's third law is that the forces are the same. Okay, so the hint I had was, don't be tricked by the difference between the size of a force and the effect it has on the object. And you have to think about what the size of the force actually is rather than the effect. So carts and show this stuff. Let me just pause for a sec here for you. All right, I got things queued up here for us. So let's go with, oops, almost had it queued up. Red pushes on the blue. So this is a situation where we're releasing energy. Okay, so I'm going to tap that little button that releases the spring. So the red cart's going to push on the blue one, and that's what's going to happen here. And so you're thinking, okay, red cart push on the blue one. That's the action force. Then of course there's a reaction force of the blue cart and the red cart, right? And so they go flying apart, right? Very equally, except for the one that like fell on the ground. Good thing it was my carts that don't have the sensors in it. I would have been more upset. Okay, supposed to pause that one before that happens. That's embarrassing. All right. This one here, blue pushes on the red. So think of the very similar reaction here, except I'm going to release the energy from the blue one. The blue one's going to push on the red one. Well, there's still a reaction force of the red one on the blue one. So it's going to be the exact same result. It does play here for us. Here we go. Right? So kick. And they go. Just didn't fall. Almost did. Didn't fall on the ground that time. So, it doesn't matter whether it's the blue pushing on the red or it's red pushing on the blue, or the blue pushing on the red. And then we have a situation where we've got a small mass going to push on a heavy mass, a large mass. Vertical is going to happen. We're going to have the blue one's going to push on the red one, and so let's just let that happen. Okay, the blue one goes flying back. The red one hardly moves. Okay, so the red one accelerates very little. The blue one accelerates a lot the other direction. What does that tell you about the sizes of the forces? Nothing, right? The action-reaction forces, so action force of blue and red will be the same as in the opposite direction as the reaction force of the red on the blue. Same size forces. That force causes this one to accelerate a little bit because it's massive. The same force causes this one to accelerate a lot because it's not as massive. Are we getting it? I think so. Feels good, smells good, tastes good, whatever. So now we're going to push on the red one, Now we're going to have the action force of the red one and the blue one. What's going to happen? Well, that force is going to make this one go a lot, accelerate a lot because it's a small mass. This one's not going to accelerate much because it's a small or larger mass, right? Here we go. Click. And exactly as expected, way more acceleration is this one due to the force than this one, only because of the different masses. The forces are the same. Hope we're good with that. I've obviously put a lot of effort in to try and make this obvious. So the roller blades one, just see which one I want to do first here. So this is a rollerblade one where we've got the medicine ball, rollerblade throwing a medicine ball. So we've got a person on rollerblades in my class back in the day. And for safety, we had time here, so we put a helmet on. But Brady's gonna throw the ball to the right, and so there's an action force of Brady on the medicine ball. So the medicine ball accelerates to the right. There is also, of course, going to be a reaction force of the medicine ball on Brady, the student, right? And so it causes Brady to accelerate a little bit to the left, and the medicine ball accelerates a lot to the right. Okay? Equal forces, different results. That's okay. We get it. Brady's more heavier than the medicine ball. And then I had a different student come up, and I said, okay, we're going to have two people on rollerblades. And I instructed jokingly, okay, so this student is going to push on this student. Okay, so a student on the right is going to push on the student on the left. I'm trying to remember his name. I know it's Brady. Anyways, it's a while ago. Brazee is the name. What was his name? Anyways, sorry, I better not. I shouldn't say the first name now. Confidentiality issues. So we have student on the right pushes on student on the left. Okay, and I instructed Brady not to push back. Just stay there like a concrete statue, And of course, that push made Brady go to the left, and the other student went to the right because of these action reaction forces, and they're about the same mass, and so they both accelerate about the same amount. Okay, so Brady didn't take part in that push at all. He just stayed like a statue, right? He didn't extend his arms, but the effect is the same. All right. So more of the same here, right? Which vehicle had the greater impact force on it? The car's crumpled up to the windshield. The truck's in bad shape, but I mean, not crumpled right to the windshield by any means, right? So which one had the greater impact force on it? They had the same impact forces, right? The effects aren't the same, but that's okay, right? Oh no. This one here, the I'll pause this so I can get this one queued up. All right, so we have in this one a train that is going to hit this little minivan. All right, and so it's a Top Gear production video here. Credit given to them. And so the question is, boom! Oh my gosh! Oh, look at that. Okay, so I have a freeze frame of that in my lesson for sure. So we have this freeze frame here of the car just getting annihilated by the train, right? Question is, which one has the greater impact force on it? And the answer, unbelievably, is that they're the same. It's just the effect of them is way different. So I'd like to think of it as if you strapped a bathroom scale to the front of the train and bathroom scale to the side of the car. If you push two bathroom scales together, they'll just read the same force. They're just one force on the other and the other force on, they're just going to have the same force on each other. So it's the same. The third law kickback here. So I need Newton's third law shotgun kickback. Newton's third law shotgun kickback. The reaction force is more obvious in this video. So we have the action force of the gun on the bullets. Obviously, they accelerate like crazy and go off to the right. The reaction force of the bullet on the gun causes kickback. Boom, right? So here we go. So that action reaction force caused it, and then the potato gun recoil. Same folder, potato gun, recoil in slow motion. We've got a reaction force obvious here. Okay, so we have got the force of the potato gun on the potato. Potato goes flying, obviously. Reaction force. 5, 4, 3, 2, 1. Boom. Huge push backwards, right? And you'll even see it in slow motion here. They're excited. Slow motion coming up. Watch that cannon accelerate backwards because of that reaction force. Okay, the forces are the same. The force on the cannon, a second kid helps hold on to it. So the acceleration that they're preventing there. The potato doesn't have anything holding it back, so it accelerates to the right. Same forces. Explain how this helicopter flies. All right, what are the forces? What causes that lift force? And so really, should be pretty easy here. We've got a force of like the blade on the air, the action force, right? So force of the propeller on the, so I'll just say the blade on the air, right? That's the action force. What you have, of course, is a reaction force of the air on the blade. So this is a reaction force of the air on the blade, right? And so that is your reaction force. And it is what causes lift, right? A lift force is that reaction force of the air on the blade. This is just a silly one, right? No surprise, they ran head on into each other, and of course there was action and reaction force pairs. This one's weird. How many physics concepts can we spot here? So it was like 3 or 4. You have the text is talking about Newton's third law, obviously. Notice the boat is getting farther back. Why is that? As it walks closer, so the person would have applied a force on the boat, and then the force on the boat from the boat on the person allows them to go forward relative to the boat, but that force backwards on the boat causes the boat to back up, right? And so on. So you think about the laws of and so on. Then there's the Doppler effect in the water waves, and obviously they're held down by gravity. And anyways, just enough there. That we don't need to watch. This is just the water jet car business. So the idea of being able to lift a vehicle here, so you've got, in this situation, you've got the force of the car structure on the water down. Reaction force is the water on the car up. All of those reaction forces up are causing it to lift. And so those are just a bunch of the same kind of scenarios there. The newest scenario that we got, I know there's a ton here, okay? A situation here is, if you look at this situation here, where we have the moon obviously orbiting the Earth, what's the force that holds the moon to the Earth? This was Newton's brilliant idea, right? When he realized, when an apple dropped on his head, he realized, oh my gosh, the force that's holding the moon to the Earth is gravity, just like the force that drags the apple, accelerates the apple towards the ground. So we have this very obvious action force of the Earth on the moon. We got pretty good earlier in this lesson of seeing that, force of A on B, reaction force would just be force of B on A. So we should be able to, at this point, say, oh, okay, well, then there's a force of the moon on the Earth. That's your reaction force. Okay, that force is real, and it's evidence. The evidence is tides. So in this situation here, you can actually see the tide get high on this end, and then it actually gets high on both ends. And you can think about why that would be. It'd be better if I freeze frame this at the moon right here. But we've got the force of the gravity on the moon, on the water that's close itself, pulling it, right? So we have the force of the Earth on the moon, and then the force of the moon on the Earth. So the force of the moon on the Earth is pulling the water up. And then this bulge over here is actually because of inertia, right? The Earth system accelerates this way a little bit because of that reaction force. I should make it green, I guess, because it's the reaction force. We have this acceleration. We have obviously the action force. If we had the moon here, we have the force of the Earth on the moon. And then we have the reaction force of the moon on the earth, right? And so this portion right here, water's left behind because it has inertia. Okay, so inertia, the water tries to stay where it was. So you get a bulge on both sides. One side because of the actual force of gravity on the water itself. So, put it that way if you want, the water on it itself. So it pulls the bulge up, and then this one's left behind because of inertia. Okay, so it's kind of easy to think of there. And so the last task is just to sort of get used to the idea of sort of complete free body diagrams. They're not really part of free body diagrams because it's on a different object, but we need to get used to the idea that this other force exists, right? And it's easy to overlook that other force because maths of the Earth is so huge, right? But basically, we know we have a force of the Earth on the person. That's your action force. So force of Earth on person. And then the reaction force would be the force of the person on the earth. Right? And so that's just a reality that it does exist, obviously. Just the earth doesn't accelerate very much or noticeably at all because it's so massive. Right? Free body diagram for the ball, we already looked at before that really there is just a gravity force on it. So we labeled these before, but we didn't go the extra mile and talk about the force of, this is force of gravity is of course the force of the earth on the ball. E for earth there, right? And then we have that reaction force of the ball on the earth, right? So those were always there. We just, we weren't wrong before because, the free body diagrams were complete, but now we're just looking at the actual third law reaction force as well, and including as a whole picture so we can understand everything about what we're doing. Same stuff here, of course, right? Got that action force down, reaction force up. Okay. So all the way along, that's always something we can do. So it's just a funny one here where obviously there's going to be lots of forces soon, but currently there's a force of the earth on the person, and there's a reaction force of down here, if it lets me, reaction force of the person up on the earth. I think I had to make that a little bigger. So, but I think we're starting to get the picture here. So all of these guys, right? So action reaction pairs of forces. We have the force of the earth down and force of the person up on the earth, right? Technically that arrow should go from the center of mass of the earth, but the earth is kind of big, okay? So that is pretty much it for that. This is a weird video called Vomit Physics where this person, you can watch the video if you want, the person tries to they talk about the idea of a fictional superhero where the person can rocket themselves around by drinking milk and vomiting milk. It's really weird. Anyways, check it out. It's kind of funny. It's fairly well done. So your questions here, obviously to state the third law of motion, and then analyzing these, right? So in each case, I helped you out in the first one here saying, okay, if you're looking at kicking a soccer ball, the action reaction pairs, obviously force of the ball on force of the foot on the ball. We're going to start with the action force. Okay, so this is the action force here. That one's easy to picture. The one that's hard to picture, we have to recognize is the opposite of that. So that's what I was saying. I started changing the order of how I show this just to make it more obvious. So please do it like that, where you're just like, okay, well, obviously we have a force of the foot on the ball, but then there's this reaction force of the ball on the foot. Okay, and so we know that reaction force that's not as obvious is the opposite direction, right? So if we flip the directions, we call that the reaction force. So all the way along, inspired by recent events here, everybody thought this was going to happen more often, I think. A ball speeding up as it's falling to the ground. We should point out, of course, there's a force of the earth on the ball. Boom, get your reaction force in there. What about this situation? The ball is tossed up. Now it has a velocity of 0 at the top. Okay, let's see that one done well. I'm definitely going to be watching for that one when I check over the questions. Hopefully get a misconception nailed out of your heads forever. There was a bunch of people that were incorrect about that kind of situation recently, and there's feedback in your lesson, so make sure to look at the feedback, please. Yeah, with directions listed. So specifically, instead of just saying the opposite direction or by showing negatives and so on, you can actually say, well, one's forward, one's backwards, one's west, one's east, and stuff like that. Okay, so if you go back, you could point out what directions were obviously implied in these situations. Spoiler alert, they're basically, well, except for the gravity ones, it's always like pushed on it forwards and the reaction force was backwards. Okay, but this, I don't want it to be something you have trouble with, just need you to recognize it. About the different sizes here. So if you have a very massive object colliding with a smaller mass, talk about the third law pair of forces, compare the values of them, explain how the accelerations can be so different, and so on. And then the question at the end about how does anything ever accelerate if there's always these pairs of equal and opposite forces? Why don't they add to zero? All right. So that is a bit longer in terms of just delivering all of the situations to help you visualize and think of all these things. But overall, hopefully we did a good job of just helping you understand it well and be able to tackle those ideas. So that is it for me. Take care. Thanks for watching. Don't forget to like and subscribe. All those things that YouTube people say. All right, bye.